A very warm good afternoon. On behalf of Nehru Planetarium, Prime Minister's Museum and Library, in collaboration with Astroculum Space Tech Research Organization, we are delighted to invite you all in today's talk. Today we'll be talking about the radio astronomy and the Sardinia Radio Telescope Italy, presented by Dr. Silvia Casu. Dr. Silvia Casu, a senior researcher at National Institute of Astrophysics, INAF, and a leading member of Astrochemistry Group, will provide a unique opportunity to explore the fascinating world of radio astronomy. She will also highlight the critical role played by the Sardinia Radio Telescope SRT in advancing modern scientific research. Dr. Casu's extensive expertise and insight will showcase how radio wave emitted by distant cosmic phenomena offer unparalleled universe information about the working of our universe. In the captivating realm of space exploration, radio astronomy is vital to uncover the mysteries of the cosmos. Unlike optical telescopes that capture visible light, radio telescopes detect radio waves emitted by celestial body. This allows us to study the distant star, galaxy, black holes, and other cosmic objects that may be hidden and invisible to the naked eye. Among the world's most advanced radio telescope, SRT, located in Sardinia, Italy, operated by INF, featured a 64-meter wide dish, making the Italy's largest antenna and one of Europe's premier instruments in radio astronomy. With the state-of-art technology, the SRT enables scientists to probe deeper into the space, pushing the boundaries of our understanding to the universe. This lecture presents a unique opportunity for space enthusiasts, researchers, and the general public to learn more about radio telescope like SRT, helping scientists to explore the vast, uncharted region of space and contribute to the global advancement in astronomy. We are once again we are delighted to host Dr. Silvia Casu, and once again we warmly welcome. It's completely a privilege to host you, ma'am, today to the planetarium platform, and I really hope that enthusiasts, students, researchers, and common public who are interested in the subject will get the deeper and better understanding about this topic. Over to you, ma'am.
Thank you so much. I'm very glad to be here with you today, and thank you really. Thank you so much to invite me because it's a very good opportunity for me to introduce some of the issues of my work in Italy at the INAFA Institute.
Yes,
So
definitely. Thank you.
So okay. So the topic of my talk this afternoon for you is a morning for me, is the Sardinia Radio Telescope, which is one of the biggest astronomical facilities in INAF in Italy. And so I'm a part of the operational team of the Sardinia Radio Telescope. And as you told you before, I'm a part of the astrochemistry and astrobiology group in Cagliari, which is the main city, the capital of the Sardinia island. So let me just give a brief introduction of the topic. When we talk about astronomy, usually we think about beautiful images and images that from which we can learn a lot of information about the sky. If you just look at these images, which is my favorite image, you can see the star forming regions, very young stars, older stars, cluster of stars and galaxies. So all the more or less, most of the objects, celestial objects that we are interested to study. But astronomy is a very peculiar science because we cannot move to this particular objects to study them. And we can study them from through the light that every day this object emit. So essentially, astronomers are, in some sense, light researchers about light behavior. So it's very important to know everything about light. I cannot, I don't want to be a lot didascalic, but it's important to notice that light is an electromagnetic wave characterized by a quantity that is called frequency, the number of the peaks in the electromagnetic waves that you can count in time unit, for example, in a second. Depending on the frequency, you can divide the electromagnetic spectrum in the different portions coming from the gamma rays. Sorry for the Italian in this picture, coming from the gamma rays to X-rays, ultraviolet, the visible one, and then infrared, microwave, and radio waves. The difference is in a frequency and, of course, in the energy that this kind of waves can bring. So the astronomy concept is to study the objects, the celestial object, in all this kind of frequencies or of wavelengths, if you prefer the concept. And it is something that we can do every day in our daily life. For example, if you want to study your hand, you just look at it and discover a lot of things using visible light. But if you are interested in the thermal circulation about your hands, you cannot just use the visible light. You have to use the infrared light. And if you suspect that one of your hand bone is broken, you are forced to use X-rays to study the situation of your bones. Okay, this is called a multi-frequency approach. That is the same things that modern astronomers do every day, starting from the visible light, like in this Milky Way pictures. You can just discover, in changing the frequency, you can discover a lot of details on our galaxy. Just changing is something like changing your glass and your filter for your eyes. Of course, there is a limitation given by the presence of the atmosphere that prevents, fortunately for our lives, from the most energetic light, X-rays, gamma rays, and a big portion of ultraviolet, but allow to the passage of the visible light, which is called the optical window, and a large portion of the radio waves. This is particularly important because it is a kind of is not only a picture of the atmosphere, but is also a picture of the development, the historical development of the astronomy, which is we start from the optical astronomy and then develop in different branches in atmosphere from infrared to gamma rays, but on Earth for the radio windows. So now in these modern days, we have a lot of different telescopes for different frequencies of the light. It's a multi-frequency astronomy. Of course, today we are talking about radio astronomy, and radio astronomy starts at the beginning of the last century, in 30 years, when the phone company, the American phone company, the Bell's company, was interested to study a kind of interference in the intercontinental connection. So they give they asked to Carl Gutte Jansky to study this kind of interference, and he built this the antenna that you can see in this picture. You can see that there are some the wheels, because it didn't know where exactly to look for study this kind of interference, and it made an extraordinary discover that this kind of waves were coming from the center of the Milky Way, of our galaxy, and so important to discover that was in the first page of the New York Times on May the 5th in 1933. Now we are used to see astronomy news on the first pages of the newspapers, but at the beginning of the last century it was not so common. So it was really an important discovery. And in some sense, we can say that radio astronomy start as a birth in this moment. Of course, then there was the Second World War and a lot of the difficulties for the radio astronomy. But the radio astronomy went very, very fast. And even if there was one of the last branch of astronomy, it has a lot of advantages. First of all, a lot of many cosmic objects, starting from the very close planets to the very distant galaxies, emit radio waves. And these radio waves can be observed 24 hours a day. So you can, it's very different from the traditional astronomy, which is limited to the night period. Again, there are little interferences with the Earth atmosphere, so the radio waves can arrive at the Earth ground with a very little distortions. And again, another advantage is that the observations are little influenced by the atmospheric condition. Of course, no astronomers can be happy to have a cloudy day to observe, I can assure you, but it is possible in a lot of frequencies to observe even if the weather conditions are not so good. And radio astronomy is a powerful branch of astronomy, which allowed us to discover new classes of objects. Just look at this particular elliptical galaxy in visible light. It's not so, it seems no interesting unless you can see in the radio range. And because it has these two important jets of plasma and radio waves coming from the center. It is an active galactic nucleus, and this kind of a galaxy are called radio galaxy. Nobody knew this kind of a galaxy before the advent of the radio astronomy. Again, radio astronomy allows us to discover other new objects. For example, look at this radio galaxy 3C31 in the VLA image. And it was first discovered in radio waves, and only after it has been identified by the Hubble Space Telescope in the visible counterparts. And last but not least, there are some radio astronomy allowed us to discover objects that were predicted by the theory, like pulsars, the pulsating radio sources. And there are fast rotating pulsating neutron stars discovered by Jocelyn Bell and Anthony Hewish in 1967. This discovery was so important that it was granted by a Nobel Prize in 1974, and it was and it couldn't be possible without radio astronomy. And again, let me. This is my research field, so I'm very happy to say that radio astronomy is a crucial astronomical range to study the molecular component of the universe. If you look at this table, there are a lot of molecules, most organic molecules discovered. Most of them are discovered thanks to the radio astronomy. Is something that is unbelievable to discover that what we can consider empty is full of atoms and molecules that are some of the prebiotic bricks of the life as we know. So from the radio astronomy to the astrobiology, the step is very short. All this stuff, all the issues can be studied with radio telescopes. All the radio telescopes are something like prototypes, very different from each other, but they are in some sense working from a very simple mathematical principle, that is the parabolic shape. The radio telescope is substantially an antenna, and the property is that every wave coming in catched by the antenna is reflected to fixed point that is called focus of the antenna. And let me see from this video how it's working. Okay, so the signal coming from celestial objects arrive to the parabolic antenna, then is reflected to the main focus of the parabola. You can put another dish in another antenna, which focus the radiation inside the antenna, where a robotic rotating system can change the path of the light, and again a beam wave guide inside the antenna can just reflect and inside the system, where the backends can transform, digitalize, and amplified and package in the signal in order to have a kind of a specific file. Let me show now some example of radio telescopes all around the world. Of course, I cannot I can not mention the Italian radio telescope. The first ones are the Noto and Medicina radio telescope, which are both 32 meters radio telescope. In Europe, there are a lot of radio telescope. I can just show you my favorite ones. The 30 meter of Iram, Sierra Nevada in Spain, which is a very awesome telescope, even if it's not very big. The biggest in Europe is the Effelsberg in Bonn, close to Bonn telescope, which is a 100-meter radio telescope. Abroad, of course, one of my favorites is the Green Bank Telescope, 100-meter telescope in West Virginia, USA. And until a few years ago, the biggest one was the Arecibo in Puerto Rico, USA telescope, which is, you can see, a fixed one. Is not a fully steerable telescope because of the dimension. The biggest one is in China and is fast, 500-meter aperture spherical telescope, the biggest radio telescope in the world. And as you can see, is again is not a fully steerable telescope because of course of the dimension. Dimension are very important because you see is a kind of a basin to catch the radio waves, and the biggest is the telescope, the most radio waves you can register and study. But of course there are some mechanical engineering limitation, and because you cannot build biggest radio telescope. So but astronomers need to have this kind of big telescopes because of the requested resolution. Resolution is the capability of a telescope to distinguish due to close objects. So a radio telescope like SRT, which is as I can show you, is is a kind of a big antenna. When observing at typical frequencies of 1 gigahertz, so 30 centimeter wavelength, thus is not able to distinguish details smaller than half the full moon because of this is intrinsic resolution, which depend on the wavelength, but it depends on the dimension. So the biggest is the telescope, the better is the resolution. But it's impossible, as I told you. So an option is, instead of build biggest telescope, to use maths. And in particular, a technique which is called radio interferometry. Radio interferometers are systems, array of telescopes that are connected, observing all the same object, and then the signal is correlated and combined to mimic a radio telescope big as the baseline of the system. The advantages of these radio interferometers are very, very important because they can give extremely accurate details about the sources the celestial sources you are studying. And the greater the number of the antennas, the greater is the sensitivity. So you can catch details and a very weak signals. So there are a lot in the last few decades, a lot of different radio interferometers have been built in the world. in here in the left part of the slide, you can see the Croce del Nord, which is the Italian is a very old radio interferometer, and is closer to the Medicina radio telescope. And again, the ex-plateau de Bure, now Noema, in Grenoble, in France, is a European. The VLA radio interferometer in USA, and the ATCA in Australia. And again, for maybe the biggest system of this kind of radio interferometer, the ALMA, the Atacama Large Millimeter Submillimeter Array in Atacama, in Chile, at about 5,000 meters above sea level. So it's a very huge array interferometer. Of course, there is now the building of the SKA, the Square Kilometer Arrays, but I cannot show you because is not complete at the moment. Is under the first phase. So this is the world contest in which SRT is situated. SRT is a 64-meter diameter antenna, so it's quite big, for 70-meter height and 3,000 tons of moving in a very precise way. I can show you in what I mean by this movement. Is a alt azimuthal equipment and mounting, because it can turn around in all for 360 grades, moving with again over this kind of wheels, and it can move the parabola thanks to this elevation wheel. And so it's a very, very precise. But SRT is a very state-of-the-art telescope with a high tech equipments. First of all, it allows a large frequency range, going from 300 megahertz to 100 gigahertz. So maybe this is one of the largest radio frequency range for a single dish antenna. And it has a frequency, it allows the frequency agility. So it's very important for astronomers. Frequency agility is a capability of the telescope to change the setup of the receivers in a very fast way. And so it's one of the state-of-the-art equipment of the SRT, but one of the best and maybe one of the most surprising technological ability is the active surface. As I told you, the efficiency of a radio telescope depends on the parabolic shape, and but when you build a big antenna, it's very difficult to keep the shape ideal, closer to the ideal one, because of a lot of deformation coming from the gravitational deformation, or coming from the different wind pressure in different portion of the antenna, or the metallic dilatation due to the temperature changes. And so instead to have a single piece for the antenna, we have a mosaic of different aluminum panels. Each of them are posed over this kind of actuators. There are some mechanical pistons that allow to change and correct the micrometric change the position of the panel in order to correct the surface shape and to adjust into the most close to the ideal one. And the presence of the active surface is very important, especially when you observe at the higher frequency, because the correction is close, the deformation can have some dimension closer to the wavelength of the observed light. So all these things to do what? To do science, of course. And SRT is an excellent an instrument and radio facility which allows a scientific excellence. It allows to study very different objects coming from the most distant, the cluster of galaxy. You can see in this picture a cluster of galaxy, and in particular the distribution of magnetic waves and magnetic field. And of course, it allows to study pulsars, so stars in a very advanced stage of their evolutionary cycle. But also the star-forming regions, and in particular the molecular component of star-forming regions. Most recently, we started to, thanks to the Italian Space Agency, we started to study also space debris or near-Earth objects. And this is maybe the last one project. We join the Breakthrough Listen project, which is a kind of evolution of the old SETI, Search for Extraterrestrial Intelligence project. Thanks to the high technology of our receiver and our backends, we can now study the center of our galaxy and exoplanets, habitable exoplanets, in order to search for possible signals emitted by an alien civilization able to connect, to communicate like our civilization. SRT has been inaugurated in 2013. And from that moment, it started, well, after a phase of scientific validation and commissioning, it started to publish a lot of, there are a lot of publications using SRT data as a single dish antenna and using interferometry. I can just put the screenshot of one of some last important publication of our groups in the last 12 months. But it's also a technological excellence because of the high technology that mounted on it. I can just show you some of the last receivers coming from Mistral, which is a millimetric camera, and a Q band receiver, which is 19 beams receiver, which I think that is one of the biggest for a single dish antenna, and W band, which allow to reach the higher frequency, like the 100 gigahertz. And then we have a simultaneous 3-band receiver that is used for radio interferometry projects. And is also, SRT is a very important radio telescope for Sardinia and for Italy, for science and for technology, but is also an important facility to connect with the territory, to connect, for example, for astronomical tourism, to develop some alternative economic way to connect with this telescope. We have a very important outreach program that in the different years that allowed us to reach different schools for any level and grade and generic public. We in the last 2 years we started to develop to organize an astronomical festival organized in the territory of that host SRT because we wanted to involve people in this research facility, and it is growing. So we are now organizing the 3rd edition. But we have a lot of different programs coming from, for example, astronomical residency schools or astronomical camps around SRT and so on. So to conclude, to close my talk, I cannot I would like to invite you to come to Italy, and in particular to Sardinia, to visit from on site the SRT. In any case, we cannot never either in the future the presence inside the entrance inside the telescope. So we are developing a kind of SRT virtual tour. You can just look at this link. Is a very basic one, but because we are updating for the new receivers images, and I think that in the 2025 spring we will release the final version of the SRT virtual tour. So I invite you to follow our webpage, srt.enough.it, or to follow in our Facebook page, Sardinia Radio Telescope Facebook page, to discover all the news about SRT. I apologize that maybe lots of things could be in Italian, but now it's very easy to translate in other language. The SRT tour with a virtual tour will be also in English, so it could be accessible to everyone. So I hope that was clear in my exposition, but I'm available now if you have a question, if you have curiosities or whatever about the SRT. I think that one of the best things is to connect with people, and so after this panoramic view about the SRT, I would like to interact with all of you. Thank you so much.
Thank you so much. First of all, ma'am, I would like to mention that the presentation was really very interestingly arranged. Also gave the detailed understanding about the SRT. Also, the topic itself, the radio astronomy. Uh, uh, we are really glad to host you on our platform, and many of the students and enthusiasts are already with us, and they have showing their interest related to the topic. So now I request people who are with us online, they have something related to the SRT, some doubts or things they wanted to clarify. This is the right time. I think you can drop your questions, and we will be taking those, and ma'am can answer and address.
Okay, I see the first question.
Yeah. Yeah.
Okay.
What is the actual process of us getting the data from radio telescopes to actually finding the celestial object, such as a pulsar? Continuation, do we trace the waves back to their source?
Okay, so for the pulsars, okay, image. Can I just come back to the
Yeah.
pulsar? Sorry. Okay, so imagine neutron star, which is the last phase of a massive star. The very last phase of his life cycle. And a neutron star is rotating, emitting two jets to this kind of two jets of radio waves. What you can observe is not the rotating signals, but something that is pulsating, and something that is I'm not sure that you are able to catch the red point. Okay, so it's something that is flat and then wow, a peak, and so on. And so the you can observe only the pulsation of the signals, and pulsars are very fast rotating objects coming from some tens for seconds, tens rounds equal in for tens, like a millisecond pulsars, and they are very precise clocks, astronomical clocks. So anything that modify the pulsating of one the pulsars is something that is related to astronomical another astronomical objects influencing the pulsation of the pulsar. What you do is observe the signal, register um, the timing of the signals, so the same frequency for different time with a very precise time resolution, and then you can infer the kind of a pulsar, the period, and so on. And again, one of the biggest dream for any pulsar astronomer is to discover binary systems. And for now, there is only a double pulsar system that has been discovered. One of my colleague, Marta Bourguet, in 2003. Yes, 2003, and with my last director, Niccolo D'Amico, and they won a Cartesio Prize for this important discovery. I don't know. Maybe I don't understand do we trace the waves back to their source question? Are you are you meaning how can we can uh, well, I don't know if I catch properly this question. Help me to understand, because the usual approach is that you point to a source, and then register the radio waves, and extract the information from the radio waves. So essentially what are looking for, unless you are making mapping, so survey of the star, and in this way, of course, you can cover a kind of field, a small field in the sky, and then from the radiation, you have to understand which kind of sources and what is happening in this survey. I don't know if I reply to your question. Uh,
So I think Ayushman Gupta has asked the question. So hope Ayushman you got the clarity. If anything you still wanted to get clarified, please feel free to write. Then we'll be again taking that question. Now we have another questions from random
okay, this is a
follow up to the previous question. What are some common beginner level
yeah,
software tools
it's
that one can use?
an interesting question because well, there is a kind of prejudice that working on astronomy is only a field for astronomers. Okay, but it's not. It is completely not. There are, of course, astronomers in astronomy, but there are a lot of different, can I say, different uh, characteristic jobs inside, because to make astronomical discoveries, you need astronomers, you need physicists, you need math people, you need engineering people, but
Interdisciplinary, actually, basically the combination of
yeah,
interdisciplinary jobs.
electronic software engineers and administrative people,
Yes,
because you have to buy
yes.
things, and communication people and so on. So if you are interested in making a career in radio astronomy, you have different options. Okay, so we have a very heterogenic group working on SRT, not only astronomers, of course. Yeah.
Uh, Shivam Sharma, ma'am, somewhere in the PPT you've mentioned the AGNs, and my question being a radio observation, anyhow significant in modeling the astrophysical plasmas.
So radio and it was significant in model. Well, you know, it's there is a strong connection between observations and theoretical work. Because it's a kind of, how can I say, a kind of cycle, you know. Theoretical models predict something that you, in principle, you should observe. Then you do the observation, and the observation can or confirm theoretical model, or put some limitations, some constraints, some borders, some constraints in the models. Again, so the theoretical models can be refined thanks to the astronomical observations, and again the cycle goes over and over and over and over. So radio observations are significant to most theoretical models, not only in the astrophysical plasma model, but in star-forming regions, for pulsars, for galactic cluster of galaxy models, and distribution of matters, and so on.
So I hope Shivam you got the clarity on your question, and I'm glad that you are here. She
Ah,
because
okay, I'm so happy. Thank you, Gupta.
also the earlier question which we have taken, yes, that is what I wanted to know. Thank you, ma'am. He
Okay.
mentioned. And like everyone, we also agree with Shivam. Really insightful academic tour to the field. We all wanted to visit the SRT site near in future, definitely.
Yes, I would be happy to to host you if you are coming to to Sardinia and show you in presence my beautiful antenna, which
definitely,
is
ma'am.
not mine, of course, but my sons used to say, "Oh, what? No, mom,"
Agree.
because
Ma'am, it will be
I spend
really,
a lot of time at SRT, so
yeah, it will
can
be
you
really glad, ma'am, if you can.
see my
Yeah.
office?
Okay.
Can
Okay.
you see?
I can just, yeah, I can see some glimpses. Ma'am, it will be great if we can, before ending the presentation today, you can share the ways in which amateur can be part of the lot of outreach work you've been doing it. As you shared on your last slides, that yes, people who are interested can join those group
Yes.
and can contribute that. So it will be really great if you can share that thing once again, so that people who have joined late can also get some understanding about those.
Okay. If in the well, if you are interested to going into detail on some of the astrophysical research fields followed by SRT, maybe we can organize another talk
Yes,
available.
definitely.
So I will be
Yes,
glad
definitely.
to 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 talk with you again.
Yeah, yeah.
In
We
any
will
case,
be
you can
definitely do that.
contact me if you have further questions. Just feel free to contact me. My email is silvia.casu at enough.it. I cannot
Silvia,
write in this chat.
ma'am,
Okay,
you,
sorry,
if you can,
I didn't put in the.
you can post in the chat.
Yeah, I don't know how to join the chat. Sorry. But if you please write in the chat my email,
Yeah, Silvia.casu
yes, at, at enough.it. And
I A I N A F
INAF
dot
dot it.
dot
IN.
in.
Mhm. In, no, not in it,
It okay.
like Italy. Sorry.
Silvia.casu INAF dot it, ma'am. IT.
IT. Exactly. Thank you,
Yes, IT.
ma'am.
Yeah, dot casu at the rate dot. Hope this email ID is
Perfect.
correct, ma'am.
Perfect. Perfect.
So I'm just highlighting this once again so that everyone can see on the broadcast. Uh, this is the email ID of Dr. Silvia Casu. So if you have anything related to the radio astronomy and SRT, feel free to write on this email ID,
Okay.
and ma'am will be happy to help you on this. I think, ma'am, on this note, I think we'll wrap today's session. It was really glad talking to you on some other topics beside radio astronomy. Today, I got an opportunity to discuss all those things with you, and in near future, we'll be happy to collaborate on all those topics which we have discussed before the broadcast, and
Yes.
also about the other career option in which young amateurs and people who are interested in subject can also join in. We'll definitely plan something in the coming future to discuss all those possibilities there. So once again, thank you, ma'am. Thank you once again.
Thank you so much.
Thank you. Have a nice day. Thank you. Bye.
You too.
Take care.
Bye. Bye. Take care.